Now that we've learned about linear approximations, we're ready for the idea of differentials. If y equals f of x, where f is a differentiable function, then the differential dx is an independent variable. That is, dx can be given the value of any real number, and the differential dy is defined in terms of dx by this equation. dy equals f prime of x dx. Now let's see what this means graphically. So if we look at our function and we look at x, and then we have a little delta x that we add to that, so we come over here to s, and then we go up and find the function. So that's at q, then we have a delta y. So we had a change in x, delta x, and then the change in y, delta y. Now we're talking about a differential dx, and that would equal delta x, but our differential dy is different than delta y, and the differential dy is actually the distance that we would change y if we had followed the tangent to the curve, or the linear approximation of the function. So as we look here, our delta x and our dx are the same, and dx called a differential, and our delta y is how much, as we moved over by delta x, how much the function changed, but our differential dy is how much the linear approximation changed. And we saw that our dy equaled f prime of x dx. So let's go ahead and look at an example to see how we would use this. Compare the values of delta y and dy if y equals f of x is x cubed plus x squared minus 2x plus 1, and x changes from 2 to 2.05. So we have our change in x is going to be 0.05, and that's also our dx. A couple things we can compute here. Actually, we're supposed to compute delta y and dy. So delta y would be our change in function value as the x changed from 2 to 2.05. So we're going to need to figure out the function value at 2. And as we put 2 in that function, we're going to have 8 plus 4 minus 4 plus 1. So that looks like that would give us a function value of 9. Now we're going to take the function and put in 2.05. So that'll be 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. And definitely get a calculator to help out here. And that looks like that's going to be 9.717625. So we can now figure out our delta y. It's going to be this 9.717625 subtract 9. So we're going to have 0.717625. Now to figure out our dy, dy equals f prime of x dx. So let's go ahead and figure out what f prime of x equals. And so we'll take a derivative. That's going to be 3x squared plus 2x minus 2 for our derivative. Now what we're going to want to do is evaluate our derivative at x, and our x was 2. So let's take our derivative at 2. So that's 3 times 2 squared plus 2 times 2 minus 2. So we've got 12 and 4, which is 16, minus 2, which is 14. So it's going to be 14 multiplied by our dx. And delta x and dx are the same, and that's 0.05. So it looks like we get 0.7. So let's compare these values. So our delta y was right here at 0.717625, and that was our actual change in the function as we went from 2 to 2.05. Our actual change in the linear approximation of the function as we go from 2 to 2.05 is going to be 0.7. We can get an idea of the error if we were doing a linear approximation. We can see how much a little change in x would affect the change in y. And actually, you see that this dy is much easier to compute than delta y, and especially if we had a complicated function. And so sometimes computing this dy, even though it's not exactly delta y, can give us an idea. Let's see what we just found graphically. So as we were looking where x was 2, and we made a little change in x, 0.05, so that's our delta x, and that's also our dx. When we computed the tangent, our dy, and got 0.7, that was the change to get here to this tangent line. And when we got the delta y, which was the 0.7 with those decimals, what that was actually what the function did. And you can see we have a little difference between the two, but this is approximately this. Look at another example. Find the differential dy and evaluate dy for the given values of x and dx. So here we have our little change in x, negative 0.1, and so we're looking to start at 1 and then go down by 0.1. So let's go ahead and compute dy. So dy equals f prime of x dx. So let's go ahead and figure out f prime of x. That's going to be 1/2 3 plus x squared to the negative 1/2. So essentially I just did a power rule here. I took this and figured it with the square root being a rational exponent. Power out in front, decrease the power by 1, and then I need to do the chain rule multiplied by the derivative of what's inside. And the derivative of what's inside here is 2x. And I can cancel these 2's. Let's go ahead and find out what this derivative is when x equals 1 then. Putting a 1 here, I would have 1 over the square root of 4. And then I need to also put a 1 for the x right here. So it looks like I get 1/2. So in computing dy, it's going to be 1/2 and then our negative 0.1, which is our dx. So that is going to be negative 0.05. So that lets us know as we change x by decreasing it by 0.1, our little change in y, negative 0.05. That's actually our dy, which is, if we had followed the linear approximation at 1, it would be how much the y changes as we followed the linear approximation at 1.